creation and size limit. That's something I cannot change, or even Judith cannot change. Is the default canvas size limit. Okay, let's get started. DFT, and so today I will just go quickly review some of the things we studied last time in DFT, and then look at the computation of DFT of an image, and then really very important concept is about circular convolution in DFT. And then if we get if you have enough time at the end, then I will start to see how we can get the DCT transform, which is an important transform in image compression and video compression from DFT. So this is the definition of the DFT, forward definition and the inverse. Okay, so for the definition of DFT, remember there are two things that you have to really keep in mind. The first one is DFT is really the discrete Fourier series definition, however, over a finite region. So the DFT has a size, and throughout our early discussions last time, we said the size of the DFT is the same as the size of the image. So we can be an MN or M by N DFT. The second thing you want to keep in mind that you can think of DFT as sampling the DTFT in the frequency domain, and then your sampling periods are the capital M and the capital N, the size of the DFT. So as a definition of the DFT, we looked at this case for the 1D, where and it's really important, many students really kind of miss this point. Why are we looking at circular convolution? How does it really fit within everything else? And I mentioned this clearly last time, and I really want to reemphasize that again. So the very basic operation is you have an input F, beautiful. Why is it not working? Okay. Okay. So you have your F as an input to our H, and then you get the output. We'll call it W for now. Now, this W is F convolve with H, right? So that's what you want to do. Now, the question is, because of the saving and the computation, because of the utilization of FFT and the modularity of the DFT, computation-wise will be much safer because of the matrix that I will show you in a minute. What we would love to do is to compute this F in here. Sorry, not this F. We want to compute this output in here by utilizing the DFT of F and the DFT of H. And the question is, if I multiply these together, and then I take the inverse DFT of the result, will this be W or not? Right? That's basically the idea, that I want to take DFT of F, DFT of H, multiply them, take the inverse DFT, and see what the output is. So the trick is really in this inverse of DFT. Does really the inverse of the DFT give us the linear convolution between F and H? And what we learned from here last time is that the answer is no. It will give you a circular convolution. And the second question that we answered last time was, if that's the case, are there constraints or conditions that we can impose on the dimensionality of the DFT, the size of the DFT, such that the output from the inverse of DFT, which is the circular convolution, is equal to the linear convolution. And that's basically the whole point in here. So we look at this simple example in the 1D case where the input is f, we have the h, and then for this slide in here, the output is g. And then we say this really look at g as the inverse DFT of capital G, which is the DFT of G. And that's basically what this equation is all about. So this is the inverse DFT, where we have 1 over n. If it's the 2D, it will be 1 over mn. Or if it's equal square image, then it's 1 over n square or m square. So this is 1 over n dimension over k, summation over k. And then we replace capital G with the product between h and f. And then we have e to the positive j 2 pi k n over n. And we went through the whole process to really get at the very end that what we get is the circular convolution, right? So this is something we did last time. Now, this is just in one slide, what is linear convolution, what is circular convolution, the difference in how you do the shift. And this is a circular shift with modularity of m and n, capital M and capital N, and this is the linear shift. Okay, so now what we did next was to say, let's now look at this under the microscope. And to do that, we would like to decouple the dimensionalities of everything that we have. So we said, let's make f dimension of capital P times Q, our impulse or our filter, the dimension of capital R times capital S. And we wrote basically what will be the output from the convolution, the linear convolution, the foundational process that's really expensive. That's why when I use DFT is this process to get the output W. So this is a linear convolution between H and F. That's what we always want, right? That's the ultimate goal to get in here. And then we know the dimensionality of W, it will be extended, it will be larger than the input F and H. And this is the dimensionality of W, right? And then, oops. And then, yeah, that slide is not here. But what we did in the last lecture, is we went through the whole derivation, and then what we found at the end is that the relationship between the output from the inverse of the DFT of the product between capital H and capital F is nothing but a tiled version of W, meaning that you take W and you keep tiling it. And the tiling, the periodicity in the tiling is the same as the dimension of your DFT or the size of DFT, which is capital M, capital N. And that basically gave us the constraints. If you don't want that overlap, then we need to choose the size of our DFT, M and N, to satisfy this condition. And remember, P times Q is dimension of F, R times S dimension of H. And then after you choose your size of the DFT, you pad both of them with zeros. You have that M by N dimension for both of them. You compute the MN DFT for both small h and small f. You do an element-wise multiplication in the DFT domain. And then you take the inverse DFT, which is again the dimension of DFT in this case. The inverse DFT is again MN, and the output will be your G, the output from the linear convolution. And we had this example last time where you have a 2 by 2. So P and Q are 2 by 2 in here. This is a 2 by 2. This one here is 2 by 2, right? So the first condition in the previous slide was what we want the dimension of the DFT to be 2 plus 2 minus 1. So to be at least 3 by 3. So we always use an even number because of the DFT. So at least this should be a 4 by 4 DFT size, right? So we know that it should be at least 3 by 3, but we go with 4 by 4 DFT. So in this specific example, we say this really makes a mistake, and then apply a 2 by 2 DFT. This is a 2 by 2 DFT. So it does not satisfy this condition, right? Which means that we will have a problem where the output of the inverse of the DFT of the product will not be equal to the output from the linear convolution. So the self-convolution output and the linear convolution output will not be the same. And then we went through the whole process of calculating the DFT of small f, and we got this one here. The same process, get the DFT of h, we got this value in here, do the product, we got this, and then we do the inverse DFT, again, is a 2 by 2 inverse DFT, and then we got this as the output, right? And that's basically our output if we use the DFT to calculate the output from this filtering. However, if you use the two-dimensional convolution, which is basically this is, to us in this process, this is the ground truth. This is what we always works. We got this output. But now between this output, 3, 2, 2, 3 is not the same as 3, 4, 2, 3. So there is this 4 and this 2. They don't really match. So there's a problem. And this slide in here, we went through it quickly last time to illustrate that. Remember that W size, because linear convolution is 3 by 3. And this is really the W. It's 132.023.001. So, and if you remember, we said if you take W and then you tile it around, right? And the tiling will be, the periodicity of it will be equal to the dimension or the size of the DFT. In this case, is 2 by 2. So if you take this, shift it to the left by 2, then the 1 will overlap here. Shift it down by 1, so this one will overlap here. Then this, you will have 2 plus 1 plus 1 as a 4. And that's how you got this mistake in here, and the issue in here. And the reason for this mismatch, which is incorrect calculation of the output G using this DFT size, is the reality that we use 2 by 2 DFT. That's basically the wrong dimension to avoid this issue in here, overlapping in the replicates. So what I told you as a practice is to use a 4 by 4 DFT. So now you pad with zeros, and then you do the same process. You calculate the DFT for F, DFT for H, 4 by 4 DFT, multiply to the inverse, then you should get a match to this number here, to this W in here. So you get 2, 3, and 3, 2. Okay, so this is really a very important concept about using the DFT to calculate the output from filtering. Questions?
I just had a question about the indices. If we could go up to the previous slide. So I see that actually the slide before that, sorry. So in this, are we indexing where 0, 0 is the top left corner, or the somewhere else? Because when I was looking, it seemed like we were indexing from a different methodology.
So I'm going through an example to give you that indices between the matrices and the calculations, and then that will help you will help answer that question.
Okay, thank you.
Okay, welcome. Yes, for padding with zeros, for this in here, we do it this way. What is? I think I have it somewhere. Yeah, as you can see, we extended this row and this row. Pad with zeros that way. But it doesn't really matter at the end of the day if you pad the other way around, as far as when you view your output, 4x4 output at the end, you know basically which row and which column you padded with zeros. As far as they are the same, the way you did it at the beginning and the way you are looking at the 4x4 at the end, that shouldn't be a problem. Okay. Okay. And then we moved on last time to look at the matrix form. And this is really something very important about why, beyond just the saving in the computation of by using DFT to calculate the output from the filtering, there is also this modularity. I remember when you do the two-dimensional convolution or even one-dimensional convolution, then those calculations in the whatever you have the terms within the summation, it all depends on your input, right? So you have to repeat the same process for any new input. And using transforms like DFT and DCT and KLT later on, maybe KLT will not have the same features as DCT and DFT, but we'll study that later. You have this kind of modularity. You have this kernel, the basis functions that define the transform, that you do the projection of the data into this space, that are independent of your input. So, and we have the example in here, and I'll try to solve an example, like a 2x2 example, just to illustrate the concept. But now, for a 4x4, if you look at the definition of the DFT, take this one here, go one more time. All right. Okay, one more. Here. If you look at this definition, this one, yes, here. Look at the definition of DFT. So the double summation, and then you have your F, which is your data. But if you look at these complex exponents, these define your basis functions. All what they depend on is basically not the values of the intensity in the input image F. All what they depend on is what is the size of my M and N, and in the indices where I am, which are M and N, small m and small n, and then which DFT coefficient we are calculating, which will be defined by the K and L, right? So we can really represent this using a matrix for a 4x4, and that matrix takes this form. Here, yes. So now for a 4x4, if I take every element and then the first one here, yeah, this one. So this is basically one element that is computing the basis functions entries in the matrix that I will use for any 4x4 DFT, meaning that it's independent of the input, right? So forget about this one here because it's depending on the definition, but this is what really matters. This one here, e to the negative j2 pi mn over m. So this is the dimension, is an m by m size DFT, right? And then these indices in here, the small m and the small n, they are the same double summation indices in the forward definition. It tells me basically where I am in that summation, right? So this is for m is equal to a 0, and this is for n equal to a 0. M is 1, n is 1, 2, 3, 2, 3 for the n. And this is my 4x4 matrix. And we've simplified this a little bit more and more. And then this is basically what this matrix is. So now this matrix in here is my kernel for my 4x4 DFT, right? So now remember, if you have an image and you want to apply a 4x4 DFT, then you can divide your image into 4x4 sub-images or blocks. And then at the same time, basically in parallel, apply this 4x4 DFT on all these blocks. And this is the formulation. So you have U, you multiply F from the right with F, and then from the left, with U, and from the right with U, right? And yeah, we'll come back to this one. So let's just very quick example where we have a 2x2 image, and then if you do the calculations for F and L, this is summation. You have M between 0 and 1, small n between 0 and 1. So these are the intermediate indices in the summation definition. And then I have F of M and N. Then I have e to the negative j 2 pi k m, and capital M is 2. And then multiplied by e to the negative j 2 pi ln, the capital M is 2 again. And so this can be simplified to be when m and n are both zeros. So these exponents will be e to the 0, that's a 1. So we'll have f of 0 and 0. And then when m is 0 and n is equal to a 1, we'll have f of 0 and 1. And then e to the negative j 2 pi over 2 km will be 1 because k is equal to m is equal to a 0. And the second one will be e to the negative j, and then this will be pi l. The third term is when m is 1 and n is equal to a 0, f1 and 0, and then e to the negative j 2 pi ln now will be equal to a 1 because n is equal to a 0, and the second one will be e to the negative j pi k. Plus finally, when both of them are 1, we'll have e to the negative j pi k, e to the negative j pi l. Okay. So now you can start to calculate what is really f of 0 and 0. Basically, what you will have is L and K, both of them are zeros. So you will have this is f of 0 and 0 plus f of 0 and 1 plus f of 1 and 0 plus f of 1 and 1. Because K and L, both of them are zeros. And then again, if f of K 0 and L is 1, then you will have f of 0 and 0 plus f of 0 and 1. And now L is equal to 1, so this is e to the negative j pi, which is negative 1. So I can simplify this to make this negative. And then I will have k is equal to a 0. So this will be equal to plus f of 1 and 0. And e to the negative j pi 0 is 1. And then finally, I will have f 1 and 1. But now I have L is equal to a 1. I have e to the negative j pi here, pi L. That will be give me a negative in here, and so on. So you can continue doing all of these operations as here to calculate. Sorry, this is capital F. Yeah, please correct this. This is capital F. This is the DFT. You can do the same thing for F1 0 and then F1 1. Now in the matrix formulation, what we had was F mu F. What is really mu in this case, or U, sorry. So it's a 2 by 2, and then I have e to the negative j 2 pi m n over 2. And then here I have e to the negative j 2 pi mn over 2. This one here, e to the negative j pi 2 pi mn over 2, e to the negative j 2 pi mn. Yeah. So the first one here, okay. So this one here simplifies to be e to the 0, that's 1. This one of them will be 0, that's a 1. One of the two, m and n, will be 0, that's 1. Both of them are 1, so we'll have e to the negative j 2 pi over 2, that's e to the negative j pi, that will be negative 1. So now our kernel for a 2 by 2 DFT is given by -1, 1, 1, negative 1. Okay. And then we can write f in here. We have f of 0. Let me just simplify this a little bit so I don't have to write the whole thing. So I can just write 0, 0, and then f 0, 1. Right. Is that what? Oh, hold on. That's my mistake. Capital F is equal to a U, F, U. So I have to write F in the middle. So that's F 0, 0, F 0, 1, F 1, 0, F 1, 1. And now for the indices, you see in the matrices, we are following the same convention we have in dpkit and MATLAB, which is the upper left corner is our 0, 0. And then on the right, we have U, which is 1, 1, 1, negative 1. And then from the right, 1 and 1, 1, negative 1. And if you do the calculations, so this here will be equal to capital F. Then if you do the calculation, what will be F of 0 and 0, or just F, K, and L. Or just the matrix, then what I will get is something like F0, 0. I'll just type it from my notes. F0, 1, F1, 0, plus F1, 1. And then here we have F0, 0, plus F0, 1, minus F1, 0, minus F1, 1. And then the second column can be negative. This is negative, yes. The second column will be F0, 0, F0, 1. F0, 1 should be negative here, plus F1, 0 minus F1, 1. And then capital F, when K equal to 1 and L equal to a 1, will be F0, 0 minus F0, 1 minus F1, 0 plus F1. The two solutions should match in this case, the matrices. So this is how you do the operations in matrix. I hope this kind of clarifies it. It's very tedious, but it's much faster. We do it in the computer, and then you can, the modularity of it, and we use quite a bit of in parallel. You can apply on a DSP chip. You can have this 8 by 8, 16 by 16 DFT. Then you do it for a whole 1K resolution image, basically in one cycle, with just in parallel, both for the entire image. So that's so far the calculations for DFT using double summation, matrix formulation, how we do the circuit convolution when we have filtering. And then this is the rest of it in here is very important because it's important for you to understand when we have an image and we have a plot of the magnitude. For now, we'll only worry about the magnitude of the DFT. If we operate on the image, either we are already multiplying the intensity by 2, we are down sampling, upsampling, or in this case, we're doing a rotation. So in here, we have this this image, and we in here, this is the DFT. This is the magnitude, the amplitude of the DFT transform, and then this is with the FFT shift. So basically, the 0, the DC is in the middle of the image in here for the DFT, and we rotate the image. What happens to the DFT? It rotates. Right away, you can see that from the spectrum. So without even looking at this image, right away you can say from the relationship between these two DFT, they are nothing but the rotated version of each other. Right? So right away you know what happened to the image. And you can prove that, and we'll just prove it for this case, for the rotation, and that will help us to bring DFT into another form, which is using polar coordinates. So what's the definition here? So we have f of k and l, double summation over small m and n. And by the way, somebody on Piazza, thanks to the students, there was 1 over n squared here. It's not wrong, but we don't really use this definition in this material. But it's not, nothing was wrong with it. But I removed it to be consistent with what we had in the previous slide. So so we have this for definition, and now we introduce these variables to write the DFT in a polar form, right? So M is R cosine theta, K is W cosine phi, N is R sine theta, and L is W omega sine phi. And then we replace M, K, N, and L with these new variables. So now our DFT, instead of it was using the rectangular Cartesian coordinates K and L, now we're using the polar coordinates omega and phi, or W and phi, right? Because that's what defines symbol K and L, right? So K and L are the Cartesian coordinates, and W and phi, or omega and phi, are the equivalent polar coordinates. And then we replace M times K and N times L with these quantities in here using this trigonometric identity. So now what do we have? We have a DFT. It's in the form of magnitude and angle. So we have polar coordinates. So what we do next is we say, let's really, in this definition, remember, this definition in here, if we rotate F with a certain angle, that means I'm changing this theta by that angle. So in this case, let's really rotate F by F naught, can be 45 degree, 20 degree, whatever. And then we plug that into the definition. Everything else in this definition is the same. We introduce this change of variable, introduce this theta tilde to be equal to theta plus theta naught. If we do that, this will simplify to theta tilde. This in here, we replace theta with theta tilde minus theta naught. And then we just rearrange the terms as in here. And what's happening in here is basically now we replace the phi with phi plus theta naught, which is the same amount of rotation that we had for the small f. So which means that if you rotate an image by a certain amount, you are rotating the DFT with the same amount. And this is how we plot the DFT. This is something just there are different ways, but this is kind of the standard de facto way, the most typical way. What we do And because I want to really get back to some other applications in here, but I want to show you this since we have been showing how do we plot this DFT, this one. Okay, so let's really prove the rotation. Okay, so we take the DFT of F. We only look at the magnitude, at least in this part of the course. And then we look at we add 1 plus logarithmic scale so that we can really reduce the range between the minimum and the maximum in these DFT coefficients. And then we try to really map everything to be between 0 and 255 using this mapping in here. And this is a flooring function. That means it gives the nearest integer, the lower end of the integer, not rounding up, but rounding down to the nearest integer. And this is basically how we plot DFT in the standard form. There are other ways, but at the end of the day, this is how we do it, at least in this dpkit and MATLAB functions. So something is really very important that I hinted to is if you look at the spectrum of a processed DFT, right? So can you have a hint about what that process is? So for example, in here, this is the DFT of the original image. This is the DFT of processed image. Without looking at this in here, so what's really happening? So what's really happening in here is that as if we are really applying some kind of a compression, we are really kind of pressuring, we are compressing, we are stretching in some direction. We are stretching the DFT in this direction, but we are pressuring it and compressing it in this direction, right? So that means I have I'm doing this kind of operation where I'm downsampling in one direction over the other, and that's basically what we are doing in here. We are really downsampling horizontally, right? Which will show up as if we are really compressing or doing this kind of operation in DFT vertically, right? Remember, we have a 90-degree between features in the spatial domain and non-zero magnitude in the frequency domain that we had in the DFT. Here is another one. If you look at the difference between the DFT of the original image and the DFT here, what you can see is that I'm adding these two lines, right? And both of them pass through the origin. So I'm really passing this kind of a very, very sharp kind of edge. And I have both of them, one vertically, one horizontally, right? And then one possible reason is I'm doing this shifting and I'm padding with zeros. So I'm adding this kind of edge in here, right? What I am missing in here in this spectrum, actually, I should have shown you the magnitude, right? The magnitude of these dimensionality. So what I'm missing is the dimension of my spectrum and the magnitudes, meaning the intensity of these DFT coefficients, because those will give you information. Because imagine I'm multiplying this image with a number 20, right? Then I'm scaling everything in the DFT with 20. The shape will look the same as this one, but if I can tell you basically the magnitude is in here, for example, it was 10, and then the new DFT of the image, it's 200, right? They will have identical shape, but from here you can right away match and say, this is really the image that I'm multiplying by 20. So these are things, and there will be a question in the exam about these things. So that's why I'm spending this time on it. Just very, very honest with you. So you can imagine all kinds of different operations I can apply to the images. What does that mean to the spectrum, for the DFT spectrum? Okay, question, Ray. Will M always equal to N for reduction? Yes, we almost for the rest of the semester, we only look at square operations with the images, mean square transforms, square convolution, mean the dimension of M and N are equal. And for DFT, DCT, usually these are M and N are even, they are the power of 2. And the main reason, but the other reason, but the main reason is really when I use FFT, it's much faster than DFT. And FFT, you can do it when you have power of 2 dimension size DFT. But yes, that's the question. M is equal to N is a square from now on. And even if you don't really have enough, imagine that you have your image and you divide the image into 8 by 8 plots. And then at the end, you don't really have the last part of the image is only 4 pixels or 4 rows. You pad the 0, so you already have 8 by 8. Or you trim, or you trim, crop your image. Here is another example of some filtering. This is the original image. This is the image after we add some random noise to it. Here is the Fourier transform, the DFT, the amplitude, the plot of the amplitude of the DFT only of this image. This is, we apply a low pass filter, and the filter meaning that I take the DFT of this image and then I apply this filter. I'm filtering out these regions, right? And then this is a much more strict one. I'm filtering more and more. And this is the output from that reconstructed image. And you can see between here and here, we lost the high frequency, is a little bit more blurry image. This is just an experiment for your own benefit. Take the image, take the magnitude of the DFT, plot the phase of the DFT, and then try to reconstruct the image using the magnitude only. You get these, especially because you get the strength of every component. If you get the phase only and reconstruct the image, especially meaning I assume the amplitudes are all equal to a 1, and then apply the inverse DFT, you get this image on the left-hand side in here. Then you just do some kind of thresholding at the end. And then here, what you really get these kind of edge components because they're really captured by the phase more than by the amplitude. Okay, so I always like to show this one here because I'm hoping this really put things together. You have the continuous time signal, f of x and y. If we do sampling, we get f of m and n. Or we do reconstruction with the sinc functions or using zero order hold or some of the other ones we studied. Then you can get a representation of continuous time signal back. If you do Fourier transform for the continuous signal, you get the discrete time Fourier transform of the discrete signal, right? Remember that's f of parentheses, not brackets, of phi and omega, which is, or f of mu and nu. These are both of them. One represent the Fourier transform of the continuous signal. The other one represent the Fourier transform of the discrete signal. Both of them are continuous in the frequency domain. If I do sampling to that, I get my DFT, right? Or I can apply DFT directly to f of m and n, and I get the DFT f of k and l in this case. And we have our notation and here, but we end almost every, we try to end every topic with these notations for clarity. Questions? C2 chat, post array. Yeah, we answered that question. Okay. Isn't it edge a high frequency component? Why did they appear on the axis? In the shifting example. Let me go to that, see. Yes, I think you're talking about this one here. These are high edge, high frequency, why they are showing up here. Yes, I mean, this is in the horizontal axis. These are high frequency regions, right? So they're showing up there. And this is basically the same thing in here. The high frequency regions, right? So they're showing up there. And actually, exactly, if for any reason, if I really enter a very thick, like black 45-degree kind of line, then you will see something like this in the DFT. Is the one in the middle a low pass filter or adding high frequency noise? Middle. I think maybe you're talking about this one. Is the one in the middle a low pass filter? I think this is not, I don't think this is the, we added, yeah, I think the correspondence, yes, we added noise here. This is not the free transform of that one. It's not, I don't believe so. Actually, maybe you're right. I think, okay, in the PowerPoint, most likely, we have it first the DFT of this noisy image, and then I added this kind of red block to say what kind of a low pass filter can be on top of it. So you're right. What we have in here is the DFT of this one here. Yes, you're right. I think in the PowerPoint I have some animation. I missed that one here. Thank you. Okay, so this concludes our discussion about DFT. Let's move on to the next transforms, and this especially DCT and DST. We'll be using these in image coding and compression. So in the next 15 minutes, I just want to introduce it, and then we can talk about it more on Thursday. So how can we go from DFT to DCT? So this is the definition of DFT standard. And now what we want to do is we'd like to have an extension to our FFMN. We'd like to have an engineered extension, because when we talk about DST on Thursday, we also have a different type of extension. So if you have different extensions, you'll get different basis functions. So we have three different extensions for f of m and n. That the first one, and I have an illustration at the next page or the one after it to illustrate what this is. So the first one is, I want to go to f of negative m minus 1 and negative n minus 1. That will be equal to f of m and n. Second one, f of negative m minus 1 and n. They are identical to f of m and n. And the third one is f of m and negative n minus 1 is equal to f of m and n. So we'd like to really have these extensions in the spatial domain space. And then one simple thing will happen is, what we would like to do, we'd like to shift the origin to be between pixels, right? And that shift means we are shifting horizontally by 0.5 pixel and vertically by 0.5 pixel. Yes, this one here hopefully will explain what that means. So the first thing is, this is my f of m and n. Is a 3x3 image or signal, and then I have only each pixel is labeled. These are not numbered, just a label with color label and the number to label it. And then I'm doing symmetric extension using the 3 extensions that I mentioned in the previous slide. These are the 3 extensions in here to get this extended image. So you can see I have a mirror around the y-axis. I have a mirror around the x-axis. And then I have a mirror here around x and y-axis. That's the first one. F of negative n minus 1 and negative n minus 1. And you can see in here, the origin was at this pixel, right, in here. What I want to do next is to shift it to be here. Okay? So I want to shift it by this amount to have this origin. So now what you see in the right-hand side, I have basically this kind of a mirrored image or extension of the image F around the y-axis and around the x-axis as well. So now if I want to write what this, the DFT of this new image, then I have to account, so everything in here changes about the limit of the sum, because now I started before from 0 to capital M minus 1. Now because of the mirroring, I'm starting from negative n to n minus 1, and from negative n to n minus 1. More importantly, I need to account for the shift in the axis by half in both horizontal and the vertical direction, right? So now I can split this summation range into 4 regions. The first one, when both of them are negative indices. This one, when m is negative but n is positive. This one, when m is positive but small n is negative. This one, if both of them are positive, meaning that in which quadrant I am, right? And then everything else is the same, like within these terms, right? So now I have 4 terms, A1, A2, A3, A4 to correspond for each one of these 4 different terms that define the DFT for this extended F. And then I just do the DFT. And you have in the notes in here, this is step by step throughout the process. We'll not really go through that. All what we're really doing, we're really changing variables. So we are defining m hat and n hat, and then using the fact that f of negative m hat minus 1 and negative n hat minus 1 is the same as f of m hat and n hat. So if we do that for A1, we get this definition here, which is what? Which is the shifted DFT for the original f before extension. We do the same thing for the second region. I will not go through the details, but I think they are self-explanatory. Same thing for A3. And then same thing for A4. And now I have closed form for each one of them. But the change of variables help me to have the same limits on the sum. I have the f of m and n that I started with. But now the ones in here in between, you have negative, negative j, positive, positive. You have positive, negative, positive, negative. So you can see the change of variables, what it really changed. Because I kept the double summation with the same limit, I have f of m and n. So these are same, but all the complex exponents are different. So if that's the case, then I really have the double summation with f of m and n as a common factor for all the 4 terms. And then I have to really have these complex exponents, like grouping them together. And if I do that with simplification, what I end up with is basically I have 2 cosines. Right? I have 2 cosines in here. I'm using the Euler's formula. For those who are a little bit rusty on that, we did this before. This is e to the j theta plus e to the negative j theta divided by 2. And then the sine theta is e to the j theta minus e to the negative j theta divided by 2j. So with this, in here, what we have is, we have the DFT of this image. The extended version of the image f is nothing but a double summation, which we have some constant for the f, m, and n. But now what this extension, this mirroring on the y-axis, mirroring the x-axis, and around the origin with that half shift, gave us a new basis functions. These basis functions, in the DFT, we used to have the complex exponents, e to the negative j 2 pi km over capital M, and e to the negative j 2 pi ln over capital N. Now we have these replaced with cosines. So we have a cosine in the m direction and a cosine in the n direction. And that's basically what the DCT is. So the DCT is an extension of the DFT when we have a specific extension of the image, the small f. And this is the definition we'll be using for DCT. There are, I can warn you again, as in DFT, there are other definitions where these can be different, this index can be different, this scalar, so online. So we'll try to stick to this one as much as we can. But again, in the questions for the exam, for example, I try not to make any question dependent on these. And in the homework, I think if you solve it other than our convention, man doesn't really penalize you for it. But try to stick to what we have in the lecture. So this is the forward definition of the DCT, and we just add a small c here just to account for DCT cosine. And here is the inverse. And C of k and C of L are defined based on what index k and L are. So C of k is half when k equal to 0. It will be 1 everywhere else. And the main concept in here is that the basis functions that we used to have them as, if you remember when we calculated U as a matrix, and we had these elements in here, they are already e to the negative j 2 pi k, mn over m or over n. Now what we have is this cosine. So we have these cosines as our basis functions. And why is that important? Because the following. Before that, I just have some examples. Again, you can see some of my former students, they love certain movies. So if you take this image and you apply the DCT for the image, and then the way we are showing the DCT image in here, this is the 0 and 0, and this is the highest frequency. So you can see we have, remember what the transform is all about? We are really looking at a transform that compact the energy in much fewer number of coefficients. If you look at this, all detail in this image, they are really compacted in coefficients that are in this region. Almost everything in here is 0. Almost everything in here is 0. Only very few coefficients in here, or a good number of coefficients, have non-zero values. And that's basically the compaction. You can see almost more than half of the coefficients are zeros. So we have a very, very good, for natural images, a very good compaction transform called DCT. What we usually do, we really apply block processing, meaning that I take a blocks of the image and apply DCT to these blocks. This one is without that block, and this one without blocks, and here with the blocks. So this one here with the 8 by 8 blocks. So what do you notice on the right-hand side? Yes, we'll study more about the DCT, and your question is correct. We look at only the real part in this case. So what do you notice about this image? So remember, we have 8 by 8 block, right? So for every single block. And now we are looking at the way we are looking for 8 by 8 block, the way we are plotting DCT. The upper left corner is the DC value, and then the frequency basically changed to the lower right corner, which has the highest frequency in both directions. So even for an image that doesn't really have much variations, it will still have a DC value that's not zero, right? And then maybe the higher frequency content will be mostly zeros. So what you see in here for all these 8 by 8 blocks in DC, what you see is really a DC. Those are the dots, the white ones. Maybe in an 8 by 8, I think this is 8 by 8. Maybe these are the only ones. So maybe only these ones will have non-zero value. Everything in here is zero. That's why you have this kind of still the DCT image. It shows you some of the information you have in the original image, which is just a fun fact because of the energy compaction and fuel coefficients in each 8 by 8. And here is basically how it looks like for the entire image, and here is for the other image in here. One concept, and then we'll get out of here. So all of these just for you. Yeah, this concept will take some time. Okay, so we'll pick this up on Thursday. So we have a lecture on Thursday. The exam will start after the lecture ends. The exam will end for all sections except Q and the ODS students on Friday at 8 p.m.
Quick question.
Yes.
Have you lectured up far enough for all the material that's currently planned to be on the exam, or will Thursday material be on the exam?
Oh, maybe you missed the first part of the lecture today. As I mentioned, the exam, the focus mainly will be on image quality assessment and DFT. And for the DFT, we will not talk about DCT in the exam. So the DCT part of today's lecture and Thursday's lecture will not be part of the exam, only the DFT. So whatever we cover in the first 1 hour today about DFT, definitely it will be in the exam. There are questions on this material in the exam, I can tell you that for sure. Welcome. Okay, guys, by tomorrow I will open the exam so you can see the instructions. And then, I will publish the exam so you can see the instructions. And then the window will open so you can take the exam Thursday after the lecture. Thank you. Have a good day. Bye.